Effect of heat. We have expansion and contraction. Expansion is coming as a result of increase in temperature, while contraction is as a result of what? Decrease in temperature. If you are reducing the temperature, expansion means we have what? Change in the dimension, increase in dimension. Contraction means decrease in the dimension. We have change of state. Is as a result of what? Effect of heat. Now a material or a substance can change its state as a result of what? Increase or decrease in heat. If you are supplying heat to it, automatically that material can melt now from solid to liquid. And if you continue to supply heat to it, you discover that, let's take for instance like water, the water starts evaporating, and which means changing of liquid to what? Vapor, another state. So then you discover that if you have any liquid and you are reducing it, you are removing it from it, which is what? Negative heat. Now you are removing it from it, you discover that it is going to change to solid, it's going to solidify. Example, cold water. You have water, if you continue to remove it from it, at the end of the day you have an ice. Then we have cracking. It can lead to what? Cracking. Cracking means failure if material is, you have you have breakage, or you have um separation between the particles of that material. That is when you said you have cracking. Thermionic emission, emission of electron from the surface of hot metal. You have change in chemical and physical properties. We've talked about this earlier on. Now let's talk about expansivity. Expansivity is the change in the dimension of a material as a result of change in temperature. Now we are talking about expansivity, change in the dimension of a material. Then the change in the dimension is as a result of thermal stress induced in the material because of heat. Let's quickly look at what's it called? Conduction of heat. You discover that conduction is as a result of what? Vibration of molecules. Now you have disturbance is taking place in the molecules of a material, let's say a solid for instance. You are supplying heat to that solid. Now there is something we call thermal stress. Now that means you are stressing the molecules, the particles of that material. You are stressing it. What are you using to stress it? You are using heat. That is what we call what? Thermal stress. Don't forget, stress is what? We have force over area, but this time around you are not just applying force, you are applying heat. So that is what we call thermal stress. And you are disturbing it. Now thermal stress will lead to what is called thermal strain. Strain means what? Change in the dimension divided by what? Original dimension. Now due to thermal stress will lead to what? Thermal strain. The material, the particles start vibrating. At the long run, we have what? Expansion due to main vibration of this material. Now thermal stress is directly proportional to the temperature difference of the material. Now you see, if you have high temperature difference, you have what? High thermal stress. So let's look at the mathematics, which means thermal stress is directly proportional to a change in the temperature. And don't forget that stress is what? Change in dimension over original dimension. That is what we have there. Now if you want to remove, using this formula, let me clean this. Using this, you want to remove the proportionality sign, the variance sign. You discover that you use equal to, and then you have a constant here, which is alpha change in theta. Thermal stress is equals to what? Alpha, thermal strain is equals to what? Alpha change in theta. Now make your theta the formula. Make your alpha the formula. Alpha will now be what? Change in, your thermal strain over change in theta. And don't forget that your strain, now this type of strain is called normal strain, and then this same strain is still what? Change in dimension over original dimension, and is as a result of what? We now call it thermal strain. Now thermal strain is change in dimension over original dimension. Now if you substitute the value of thermal strain here, this strain here, into this formula, you get this. That is how we derive that formula, which means alpha. Alpha means what? Coefficient of expansion is equals to what? Change in the dimension over original dimension multiplied by change in temperature. That is what we have here. At the end of the day, you have d2 minus d1 over d1 into bracket c2 minus t1. This is the definition of all the terms here. That's about coefficient of expansivity. Now, the first coefficient of expansivity is linear expansivity. Coefficient of linear expansivity is the change in the length per unit change in temperature. It is denoted by alpha. Now, this alpha that I use here, I just use it to derive. I just talk about the coefficient of expansion. I'm not talking about linear. I just use it as a symbol just to explain how we derive the formula. Now, the actual alpha here is what? Coefficient of linear expansivity, which is the change in length per unit change in temperature. It is denoted by what? By alpha. It varies with different material due to different atomic structure. Now, if you are talking about coefficient of expansivity, it is a property of material. Let's take for instance, if you are subjecting aluminum, copper, steel, brass, you have the same length, and then you are supplying it to them at the same temperature, you discover that their expansion will be different due to what? Due to atomic structure and all their atomic properties, because they are different. So that is why we have different material have different. That is the reason why different materials what? Different coefficients of expansivity. Example, coefficient of linear expansivity. Now, using that same formula here, you just change your dimension to L. You have alpha is equals to change in L over L1 into bracket change in theta. At the end of the day, you have something like this. Now look at the diagram. One dimension, initial length, final length. Look at all this. L2 minus L1, L1 initial length. All right, let's forge ahead. Area expansivity as well. Now, area expansivity is also simple. Is the coefficient of area expansivity is the change in area per unit length per unit change in temperature. It is denoted by what? Beta. It varies with different material due to different atomic structure. Now we have this as well. The same thing applicable to linear expansivity. Here we have beta instead of having alpha. You have your initial area and the final area. You discover that the two dimension has changed. This dimension increase and this dimension also increases. So that is that about area. The last one is volume expansivity. Now, coefficient of volume expansivity, here we're supposed to have volume expansivity is the change in volume per unit change in temperature. It is denoted by gamma, small letter gamma. It varies with different material due to different atomic structure. Now look at it. You have gamma is equals to change in V over V1 change in theta. You have your formula here. Look at the dimension. You see that the 3-dimension has changed. Now we have expansivity of liquid. Consequence of expansion. The first one is undesirable expansion. Expansion of rail lines, bridges will lead to buckling and failure. In order to avoid this, adequate provision is made for expansion of bridges and rail lines. I will quickly explain this. We also have what? Sagging of overhead cables. Now, consequence of expansion. Now, due to the fact that as temperature increases, we have many things that are expanding. Let's take for instance, you have your bridges or overhead bridge, and this bridge will expand. Now, adequate provision must be made while designing bridge. So you have to leave some gap so that when this bridge is increasing, is expanding, so this bridge will not buckle up. So that is why most time, if you have ever passed on, maybe you have you pass on a what overhead bridge, you will see that you have some space in between them. So they provide that space for expansion of the bridge. Peradventure, the bridge will expand so that the bridge will not what will not swell up, will not buckle up. The same thing with what rail lines. They will give a gap for what for expansion. Another disadvantages of what or consequence of expansion is sagging of overhead cables. Over time, all those aluminum cable, they will sag, they will come down due to what? Due to expansion. So that's another disadvantage or consequence of expansion overhead cables. We also have cracking of glass. You pour hot water inside your glass, you and the likes, and at the end of the day, you see that it cracks. So these are due to what? Expansion. You freeze a bottle inside the what? You are inside your deep freezer. After a while, you discover that your bottle starts breaking. So it is due to what? Contraction and expansion. It is due to contraction and expansion. Basically, if you have any water inside a liquid, no, let me explain. I will still explain this later on. Now let's look at expansion of clock wheel. I think question used to come out on this. Expansion of clock wheel due to increase in ambient temperature. Ambient means what? Environment. Ambient temperature, surrounding temperature, or ambient temperature. Now, due to ambient temperature in summer, the clock loses time and the clock gains time in winter. Now, the clock loses time in summer. Summer period means the period that we have increase in temperature, increase in ambient temperature. Now, due to this increase in temperature, your clock wheel will automatically expand. And due to the expansion, the rate at which your clock is moving. Now, if your clock is moving, then let's say the minutes, the seconds is actually moving. It has a standard, it has a constant rate at which as it is swinging. It swings, it swing, and then you have what 1 second. Now, due to the expansion, it will swing and it's not going to reach that particular place again. So we have a mechanism in which we use to what to counterbalance the effect of what the effect of expansion during summer. We have it in our clock, our what's it called, analog clock. We have them. The same thing used to happen in winter. During winter, we have what lower temperature, and this is what due to contraction. So automatically, your clock will gain time. So what the action point here is, clock loses time in summer and clock gains time in winter. In order to avoid this, a bimetallic strip mechanism is used to counterbalance the effect of expansion and contraction. Now, this bimetallic strip that is used will counterbalance it. We counterbalance the effect. Application of expansion. And the first application we have here is a diagram of electric fire alarm. Now you have a bimetallic strip here. You have a copper and an iron. Now copper is having high coefficient of what? Thermal expansivity, which means that thermal will expand, copper will expand the more compared to iron at the same temperature gradient. So which means copper will expand the more, we change in length, in volume, in area, the more compared to what? To iron. So you have a point here, you have a mechanism here. Now don't forget, this is what? Electric fire alarm. What we are doing here is we have an open circuit here. This is an open circuit. Current is not going to flow to this device, to this alarm. Now we have a sufficient space will be given here. Don't forget, iron is a what? Is a conductor. Now to complete the circuit, we must have a contact between, there must always be a contact between this and this to complete the circuit for this alarm to work. If you want this alarm to work, there must be what? There must be contact. There must be contact between this iron and this guy here, this melter here. Now, since it is an electric fire alarm, you have it in your, what's it called, in your house, in a factory. They basically use this in a factory. But the funniest part of it is technology has advanced. They are not using all these type of uh, electric fire alarm again. We are using a sensor, using sensor, thermistor, and the likes. They are using it that can easily sense change in temperature, and the signal will be sent. We have a programming language. We have a programmable, what's it called, a programmable alarm that will immediately it senses a temperature that is beyond the normal temperature. The alarm starts working. Wow, 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 and everybody will know that something is wrong compared to this one, because this one will waste a lot of time. Yeah, let me explain it. Now, as the temperature increases, the iron expand more than, the copper expand more than the iron. So we have a bend. So this thing is going to bend, and a contact will be made between this iron and this conductor here. So automatically the circuit is completed and this mechanism will work. You can look at the hand. You see that we have a gong here, and it will strike this thing here, and sound will be produced. Wow, 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 wow. Then we use it for what? Electric fire alarm. Another application which here is called thermostat, and thermostat is just like your electric fire alarm. The difference here is we are using this to open and close circuits. For instance, if you have an element, let's talk about our iron at home. Now your iron, if there is no mechanisms that will stop the flow of current to that element, that particular thing that is giving us heat in our iron is known as element. That element, if there is nothing that will stop the control of current, that thing will continuously increase temperature. That means that thing will the iron will be burning our clothes. If we don't have any device that will checkmate the current that is getting to the element. The same thing with our cooker, our electric cooker. If you don't have any device that will stop the flow of current, we discover that that thing is very dangerous. The thing will just start in the temperature will just be increasing continuously, and if we don't have anything that will absorb the heat, the next thing you are going to get is, I've tried it, the next thing you are going to get is explosion, and that thing will get damaged. The same thing with our boiling ring. Now a boiling ring is not having, I don't know if any one of you have ever used a boiling ring. Now, a boiling ring is not having a thermostat. I tried it when I was very young. I removed the boiling ring from the water, then I plug it. Then I start observing the redness of that boiling ring. After a while, I heard a sound. Pop. Now, do you know what caused it? It is as a result of what? There is no device that will checkmate the flow of currents, and that thing keep on increasing in temperature. Is generating heat, and there is nothing that will take away that heat. If you have it inside water, the water will be taking the heat. The water will be taking the heat. That is why we call it boiling ring. The water will be taking the heat. So we have no effect. Now this time around, I remove it and I start observing it. It's very dangerous. Don't try it. Something that is very dangerous. No, so the device that checkmates, that controls the amount of current that gets to that thing, is known as what? The thermostat. It's just like it's going to be shorting the circuit. Sorry, it's going to be opening the circuit, not just shorting the circuit. It's going to be opening the circuit at an interval. Let's look at the mechanism. Now we have two type of melters here, and then it's going to be connected with the heating element to the heater. Then we have a knob here that you can adjust. Now there is a contact here. We have a contact here. Sufficient gap will be left. Yeah, and so we have sufficient gap here. So as your iron is working, the temperature will be what? Will be increased. Don't forget that iron and brass. Now, as the temperature is increasing, so this thing will be bending, and it will get to a point there will be a sufficient gap will be left here. You have a sufficient gap here left here, then we have an open circuit. Your device will stop working again. You are going to hear the sound like pa, and your iron will stop working. After a while, let's say like few seconds, this thing will cool down again and return back to its original shape, and there will be a contact again. Current will flow to that heater again. Then you can adjust the gap. So we use this knob to adjust the gap. So which means that if you want your iron to be taking more current, that means you want the iron to be very hot. As you are turning this knob, there is a contact here again. This thing will push this guy here closer to this. So the gap in between the gap in between this and this, which means this gap will reduce, will be so minimal that for your iron to for you to have a sufficient amount of contact, a gap between these, the temperature has to increase to an extent that the expansion of this thing has to be more. So that is the working principle. The same thing, we use this thermostat in refrigerator as well, in our cooker, in iron. We also have it in combustion engine as well. We have it in a combustion engine. Another application is bimetallic strip. You have it here. Now let's talk about this diagram. I used to see question under this diagram. We have brass and steel. Brass is having high coefficient of expansion compared to steel. That is why you have this diagram. So at high temperature, the brass is going to expand the more compared to steel. So if you cool it down as well, you have this. So you see that cooling it down as well, you have this. Increasing the temperature, you have this. Your brass expand the more. Cooling it down, your brass contrast the more. That is just it. Cooling, your brass contrast the more. It shortens in the length compared to your steel. Heating, it increases in length the more compared to your steel. What you need to know here is when you are going to have this, and when you are going to have this, and when you are going to have this. When you are heating it, your brass, because of the high coefficient of expansion, your brass expand the more. So the one that is outside, we have the length of the length of an arc of this guy will increase the more compared to this one. Will be so more compared to this one. The same thing, the length of an arc for this one will be so small. Contraction means what? You are reducing the length. So the length of this guy will be so reduced. The reduction will be so much, will be greater than this. So just try and know the diagram. The same thing with what? Iron and steel. Let's talk about anomalous behavior of water. Anomalous behavior of water. Water becomes denser as it approaches freezing point. Water reaches its maximum density at 4 degrees Celsius. Below 4 degrees Celsius, water expands as it freezes, leading to ice being less dense than liquid water. Question can come out on this, just this alone. I used to see question, just this alone. Now, water becomes denser at a temperature as it approach freezing point. Water reaches its maximum density at 4 degrees Celsius. Now, if you are increasing, let me quickly read this and I will explain. Let me read everything here, then I will explain it. Water becomes denser as I've read that. Below 4 degrees Celsius, water expands as it freezes, leading to ice being less dense than liquid. This expansion is due to hexagonal lattice structure of ice, which occupies more volume than the random arrangement of water molecules. The abnormality in the properties of water to expand instead of contract at a temperature below 4 degrees Celsius is called anomalous behavior of water. Generally, if you are increasing the temperature of any substance, that substance is expected to increase in volume. And if you are reducing the temperature, it is expected of that substance to what? To reduce in volume. That's contraction. You get contraction while you are reducing temperature. You get expansion while you are increasing temperature. Now for water, it's the other way around. Now water will behave like all other substances. When what the abnormality in property of water to expand instead of contract, which means if you are increasing the temperature of water, the water will expand normally. But when you are reducing the temperature, the water will still be behaving normally, but it will until it gets to 4 degrees Celsius. So which means if you are reducing the temperature of water, the water will start contracting as it gets to what? 4 degrees Celsius. Now when it gets to 4 degrees Celsius, let's look at this. Let me use the diagram to explain. If we are increasing temperature like this, don't forget we have what? Temperature increasing like this. This is the volume. You discover that you are increasing the temperature, the volume what? The volume is increasing. Looking at this graph, increasing, going like this, you see that the volume is what? Increasing. But when you are coming down, you are reducing it. You see that the volume is also reducing as well. Initially, if you are moving forward, the volume is increasing. Now you are coming back, the volume is reducing. So it is expected your normal graph should look like this, coming down like this. So which means going up, volume coming up. Let me clean your normal graph should look like that. So moving like this, your volume is going up. Coming like this, which means reducing temperature, your volume is coming down. But you observe something here. You are going to observe something here. You will observe something there at this 4 degrees Celsius. You observe something. Now, as you are increasing temperature here, normally you see that the volume is what? Increasing. Now, if you are coming down, you are reducing temperature. You discover that the volume is also what? Reducing normally. But when it gets to 4 degrees Celsius, you will now discover that the volume starts changing again, starts increasing, which is very abnormal. Now, this abnormality is known as what? Anomalous behavior of water. And the explanation is here due to what? Lattice structure. We have hexagonal lattice structure of water, of ice. That will make the ice what? To occupy more volume. So, and as a result of this, the water starts expanding again instead of contraction. When I was explaining this, I used this sachet water to explain to my student the reason why if you freeze your water, you have a normal water, and you freeze it, you discover that if it has turned to ice and then the ice melts again, and if you now look at the sachet water, you discover that it will look as if the volume have actually reduced, the volume of the water. Now the reason is due to anomalous behavior of water. As the volume is, as you are reducing the temperature, you are cooling your water. The water will start contracting, the volume will be changing. will be reducing, but when it gets to 4, that is when expansion will now take place again. At 4 degrees Celsius, don't forget that you have a water occupying the volume of your sachet or the volume of the nylon. Now the water volume will start increasing again, which means that the nylon will also expand. When it now turns to ice, the ice expand the more. It has increased the size of your nylon, and this time around the temperature is now increased again. The ice now turns to water again, and don't forget that the volume of the nylon has increased. So that is why, and the water now returns back to original volume again. You now have what? It will now look as if your water has reduced in volume. It is due to what? Anomalous behavior of water.